We'll get to know them and what they do, and then together we will discuss where we want to go. So the panel is called Quantum Technology, what we want to do, where we want to go. And of course it's open to all of us. And chairing this panel will be Dr. Rocio Harry.
Thank you. Now, to start the discussion, perhaps you have some ideas you want to start with in the order you would prefer. Asaf, you give your name and where do you work.
No, it's perfect. So we're doing.
Your name?
Yeah, so I'm Asaf Paris, or Asaf Paris. So I've been working in Mexico for a bit more than 2 years, setting up a new experiment. So I have a bit of experience, not the most experience of how it is to set up an experiment in Mexico. I've seen a lot of how, like the social, like the bureaucracy and the. I haven't had to deal so much. Well, I had a lot of help about getting funding, so that has been great. But I know it's not always easy, and well, I think I will leave my presentation there.
Okay.
Well, since I give a talk, I think most of you know me. I'm Laura Rosales. I'm from Centro de Investigaciones en Óptica. I work on quantum optics, quantum information, and ultra-cold atoms, and field theory, mostly of entanglement, nuclear steering, and Legare inequalities, Gaussian inequalities, and most of you heard my talk in the yesterday. So now I think, like Asaf, I give the voice to Karina.
Hi, my name is Karina Garay. I am from Centro de Investigación Científica y de Educación Superior de Ensenada, in Ensenada, Baja California. I am responsible of the nonlinear interaction quantum optics laboratory, which is part of Landmark. In this laboratory, we do research concerning non-classical light, the generation and manipulation of non-classical light, particularly based on spontaneous four-way mixing. I don't know. And nowadays, we are starting with a new project with the idea we are working on are the develop a quantum gate based on nonlinear optics. We also are trying to develop or implement a protocol for quantum teleportation.
Hi, I'm Roberto Belán Montiel. I'm a researcher at the Institute of Nuclear Sciences, Instituto de Ciencias Nucleares at UNAM. I'm also the current chair of the Quantum Computing and Communication Technical Group of the Optical Society of America. And basically, the research that my group does is something at the interface of quantum optics, chemical physics, and biology. So it's in general, or in one sentence, we are trying to develop quantum optics techniques applied to chemistry and biology. So that's more or less what my lab is doing. I'm also building a lab, which the title is something like Laboratorio de Micro y Nanofotónica. So it's something in between the micro and nanophotonics. So that's more or less what we're doing.
Maybe I should amend my presentation because I forgot to say. So I work at the Institute of Physics at UNAM. Also, that the lab that, we're building together with help of some students is the Rydberg Quantum Optics Laboratory that Rocio introduced as part of the Laboratorio Nacional de Materia Cuántica. And what we want to do is work on tools that will help us to leverage the strong interactions that are existent between Rydberg atoms, to map them to light and be able to manipulate light at the few photon level. Yeah.
Okay. Then perhaps Roberto, because you are the computing man. Here they ask, yesterday we have been told we are far away of having a quantum computer. But what about an analog quantum computer. Seems we are not far away from having analog simulations of condensed matter systems, ultra-cold atoms.
Well, 2 days ago, if you look at the news, there was a paper in Nature by Google that says that they somehow tested a quantum supremacy, showing some calculation that couldn't be reached using classical computation. But there is some answer from IBM saying that no, that they have a computer that can be done in 2 days. So there's still some developing a lot of algorithms. He's in Max Planck for quantum optics. And he says that if they keep pushing it, then for sure there will be a quantum computer. But yeah, I mean, I don't know that's the question related to, because analog computing, it's basic. Well, it can be divided. No, I don't know if it's thinking of like digital computing or analog computing, but those two can be done because you can use a quantum computer and perform analog computation or a digital computation. But if we are thinking of some classical analogs to this quantum computation, then we have those. But one thing that we know is that not all algorithms will work in this type of simulators. So
Perhaps Jorge wants to say something about that.
I think they probably mean simulating.
Yes, the quantum simulation.
Yeah, I mean using cold atoms to simulate other Hamiltonians.
Yeah,
Also,
so
like this, also Karina, like the artificial magnetic fields and using all kinds of.
so I am the improvised guest. But no, what I can say here is that I think that it's very important to distinguish between quantum simulation and quantum computing are not by no means the same thing. Okay, so in quantum computing, I'm not a specialist on that, but what you do is that you use quantum mechanics to manipulate and encode information in quantum objects. And one of the main ingredients is entanglement. In quantum simulation, you have none of that. Okay, so for instance, a very good system to implement quantum simulators are cold atoms, and this is because cold atoms are very controllable systems, because you can control their thermodynamic properties, you can control their geometry, their dimensionality, the quantum statistics, many things, the interactions. So in general, ultra-cold atoms are many-body systems with a degree of control that I don't think any other many-body system has. So in particular, for instance, in the case of simulating condensed matter systems, what you can do is that using light, we had a lot of talks showing how much control you can have in producing light with different shapes, just in the talk of Rocio, we saw that. You can create a periodical potential in 3 dimensions, and then put few atoms in each side of this periodic potential, and then you have something very similar to a solid, but this solid is made out of light, and instead of having electrons, you have cold atoms, which are way more controllable than electrons are. So then you can implement a specific Hamiltonian into this system and make the system to behave as if it were solid, but with no imperfection, with no impurities. So you can simulate other systems using cold atoms. Okay? So this is how I understand quantum simulation, at least using cold atoms, and as you can see, it's very different from what Google made with this quantum supremacy algorithm.
There's another question here. Can you define or try to define what are classical and quantum technologies and what are the difference between them? For example, in my living room, I have a quantum whatever that is, a television from Samsung. Is that quantum technology? Who wants to answer?
Yeah, maybe. I mean, we do need quantum mechanics, understand a bit of quantum mechanics to be able to develop such a television. I mean, the fact that they call it quantum dot and quantum, that's all marketing, but still, without the development of that's. I think that's what Luis Orozco was talking yesterday about quantum. I mean, quantum 1, quantum 1.0, quantum 2.0, and well, the first quantum revolution.
Okay. When we talk about quantum technology, we refer to technology we are based which are based on quantum mechanics. We applied systems with properties which don't have a counterpart in classical mechanics. And they are, in my opinion, based on two properties. One of them is superposition. We have superposition of two properties or states of the same system, and another one is quantum entanglement, which is a property that gives you the opportunity to have two subsystems which are in some way prepared, entangled, and if we can send one of them far apart, if we do some operation, this affects the another one independently of the distance between them. That's two properties I think are the main difference between the system, the classical systems, and the quantum system in which the quantum technologies are based. I don't know.
Well, I don't know if it's too simplistic, the answer, but we cannot forget that computers right now are using bits, so it's a classical way of sending 5 volts, 0 volts, or whatever. So we have two possible states. Doesn't matter if we are using some quantum effect for storing information or whatever, but the computers that we have now, they will have some definite values, so zeros and one, just going into the basic definition of a bit. For qubits, and also these computers, imagine that you want to sum 1 plus 1 plus 1 plus 1 to get the 4. The computer will produce some intermediate operations. So the computer needs to check what's 1 plus 1, and it gets the 2, 2 plus 1, 3, and so on, and gets the 4. The difference with a quantum computer, but as I see it, if I'm wrong, please correct me. The idea is that if I have a quantum bit, then that's this superposition of these two possible states, the 0 and 1. And the difference, at least for the, let's say, analog computation, will be like, if you want to sum 1 plus 1 plus 1 plus 1, the quantum computer will tell you, well, the most probable answer is 4. And it doesn't require steps in the calculation. So that's probably why, that's where the difference lies. It's in the that is not needed these intermediate measurements, no? Otherwise we lose our wave function. So that's probably, if we go to the basics, that's the basic difference, no? The 0 and 1, or the possibility of having these superpositions.
There's another question here, but I want to do a question before to you. No, the panel is entitled that what do we want to do about quantum technologies? So, for instance, Karina, what do you want to do about quantum technology?
Okay, as I already told, I have been studying the process of generation of photon pairs by means of nonlinear optics. I understand when that process we can engineer the process, and a few years ago when I started equipping the lab, I thought that it's time to go forward and apply this. And that's why currently I am trying to develop this quantum gate, which is part of quantum computation. but for this we need to start new collaboration because I have expertise in quantum optics, but in order to construct this or implement to this gate, we need nanofabrication, microfabrication, new materials in order to get the best the system for that. So specifically in my group, we are trying to, or we are starting to implement a quantum gate, but not quantum gate based on linear optics, which is the most common. We are trying to use different degree of freedom of light. In this case, it is time. This quantum gate exploit nonlinear interaction, specifically frequency conversion in nonlinear crystal or Ki-3 nonlinear materials such as waveguides. And in this, we can generate single photon wave packets. These wave packets exhibit temporal or spectral structure, and we can express this data structure in the based on temporal mode. And with those temporal modes, we can define a basis for encode information. So that is that we are trying to do right now.
Roberto, are you trying to do something specific about quantum technology?
Well, I don't know, just following with your question, I think we have a lot to learn from at least from the US Quantum National Initiative. You see that if you read the act that was signed in December 21st, there are like 7 lines which are important. And if you look at that, it's kind of looking at the big picture. It's not like looking for like individual goals, but it's like you produce a packet that will tell you, well, you will have different goals. And how you get to those goals, you need to create an infrastructure that can be accessed by everybody. So that's a good thing. And if you look at those lines, then you will see that there are 4 points which are experimental and 3 of them which are theoretical. So you need the power of the two areas. It's important, one area which is now very, very important and is getting a lot of heat, it's quantum sensing. So developing sensors is something that is very, very important. Of course, quantum networks is something that is really important because there's people is trying to get some quantum internet, this quantum network. So devising different devices for communication, for computing this transaction problem, which is like Jorge was mentioning. There's some computation in the cold atoms or in the superconducting qubits or whatever, but that information has to be sent somewhere else. And that information will go through photons. So there is some problem there to connect electronics with light. And yeah, so that's probably what we need to look for, like something that surrounds all the ideas and not looking for specific ideas. And one important thing that I believe we should look at is trying to develop new programs in schools, universities, or even graduate programs devoted to quantum engineering. Because that is a very important line, to create people who is familiar with quantum algorithms. Because right now, it's like physicists we're trying, or engineers are trying to get into quantum, but I think it's necessary to create a program for developing quantum engineers. So I think that's something that...
Okay, but in Mexico?
No, in Mexico.
But in particular?
Yeah. To create programs to
the last part is easy, but the other ones...
Well, the other ones, it's the same, no? We have to take all the talent here and look at the specific abilities or skills that everybody has and develop something that is general.
Okay. Asa?
I was thinking that, the workshop is called Quantum Technologies, and there's been a lot of initiatives about quantum technologies, but it's never really clear what quantum technologies really mean. And also yesterday there's talk about technologies that take advantage of these principles of superposition and entanglement, but many of the quantum technologies that have been popping around and have been advertised are not really related to this. Sometimes are just related to new technologies based on atomic properties. For example, I don't know, I think that like a quintessential example of this is the atomic clock. As we've been told, it is, one requires superposition to really do this interferometry and do it very carefully. But there are also, let's say, more mundane atomic clocks one can buy, and they're not based on this. And they're called quantum technologies. Also, a new kind of self-calibrated electric field sensors are also like a new kind of quantum technologies. And many of the things that are being called quantum technologies are new technologies based on quantum properties that are not necessarily based on entanglement or superposition, but rather in the discrete nature of some atomic system, for example.
Now the question. Here it says, Moshi said about applying quantum mechanics to technological advances, but there are still many questions about foundations. Which is the outlook about discerning entanglement, quantum superposition, etc.? Laura, do you have any comment?
Well, that's a very good question because I used to work with Margaret Reed, and she works a lot in foundation of quantum mechanics. And the thing is that we have many types of entanglement, right? Like the usual entanglement that we talk about, but we also have EPR steering that I talked yesterday. But every time we see in theory, we have this, I try to make a picture, like it goes like a triangle. Well, sometimes it's goes like a Venn diagram, like we have entanglement here, then a subset of EPR steering, and then a subset that is Venn non-local states. So that not all entanglement is the same, and how can we differentiate these three types of entanglement? But there is also another type of picture that it looks like, let's see if I can draw it. It looks like a triangle, and then we have the states that are classical, then the common entanglement, then the steering, then non-local states, and then something called quantum discord. I cannot talk a lot of quantum discord because I usually don't define things that I'm not sure about, but these are words that we're talking about. And another thing that is in foundation, that how can we differentiate all these things that I'm talking to it about, is when the terms coherence come as well, because how can we relate coherence with entanglement? So the working foundation is these three things that I talk about: entanglement, steering, and non-local states that can be defined in terms of falsifying a local hidden variable theory, falsifying a local hidden variable state, and that we cannot factorize a state. Do I lose everyone here? No, I know. Or I'm okay.
Hello.
Okay. Because I see some faces that I lose them. Okay. So the work here in the question of if there is still work of this non-local correlation, yes, it is. And every time we can try to not only define it theoretically, but the thing is how can we also show them experimentally. So I think I stop there.
Jorge, do you want to add anything?
Okay, I don't want to do a very long contribution, but concerning this question, I think it's fundamental that we keep doing, let's say, basic physics and basic science. So I know that the tendencies is, not only in Mexico but around the world, is to always say what we are doing is useful for, what's the application, what I can do with it. And of course, it's very important. This is very, very important, but I think that as in the beginning of the question, we never should stop doing basic science. without asking us as a driving question what I can do with this or what can be the application. I think that one part of the job of research is just simply to understand the universe, how the things work, and I'm sure later somebody will figure out what we can do with that.
Okay. So I don't know if anyone has a question, even if it was not written in the paper. Anyone start? Yes, sí, me parece que ya. Is there any question I haven't asked? How much money we need for a quantum computer? Sorry. Do you know?
Well, I have an idea.
No. It's not really quantum, but I think it's like 20 million, the wave or something like that. IBM hasn't released a price for the wave or something.
Okay.
Not to do it, but to buy that thing, that machine.
Karina, do you want to add anything?
Here there was something around 20 million for D-Wave, which is something that is commercially
It's
available.
okay, no?
But that's the one that has a price. IBM hasn't released any. They have shown.
Do you have any other comment you want to make?
Well, about fundamental science or basic science, which is now a term that is sounding a lot around in Mexico. I think the only comment I have for that is that we have to keep a healthy balance between fundamental science and applications and development of technologies. I mean, we cannot forget any of those two. So some time ago I heard in a workshop that some people say, well, I like doing fundamental sciences, but you know, in the privates have some money, so we have to look at companies as well. I mean, that's the way we can get into funding. No, we can get some money, then do some technology, and while doing that technology, we get equipment, and then do some fundamental science. But I think there has to be some healthy balance between those two. We should never forget about the two things.
Karina, Jorge, anything to add? Asad?
I saw that there was a question.
Sorry, I didn't see.
Well, I'm very happy to hear you together. I can see many different points of views. But my question is, you say what we need, but I would like to hear, as Roberto was saying, how you can do it. How do you have any ideas? Because following what Rocio was saying, it was a really big effort to construct one big laboratory of quantum mechanics in the country, but we don't need one, we need many more. So do you have any idea of how to reach this goal with the government? Because, well, now the government is totally closed, or it seems to be closed, because this is not like main importance for the country, right? But we need to show that, yes, it's important. So I don't know if you have any ideas.
I think that the main thing we have is resources. I have seen bachelor students doing something that in other countries do the postdocs, honestly. When I saw how Jorge and Daniel and everyone has started a lab from nothing, and I have seen how the people work all the day because they are dreaming of getting something, that is the main resource we have. We know that there will be hard times, we know, sorry, and we have to follow, but we have done something that we can continue, and I will be very happy if we continue working in the same way, trying to do a synergy, a real synergy, and collaborating and using our students. Most people's work is looking for students because our students work very, very well. Yes, and we have to do that. That is what we have. Anything else?
And maybe I should clarify. I mean that the national lab is not one lab. It's actually like 11, between 11 and 15 labs. It depends.
Yeah, I would like to add something to this. I'm a little bit pessimistic, or maybe realistic, but I think that there is an international formula that has been tested in many countries in the world, and it's an approved formula that we know it works. I don't know if it is the only way we can do things, but it's, and I think that there is a threshold investment that a country has to do in order to make the science that this country produces useful and economical profitable. And this threshold is more or less 1% of the PI, I don't know how to say, the brute internal product, the gross internal product, gross PIFC. Okay, so if Mexico doesn't increase the amount of money that is investing in science up to this percentage or more, I'm really pessimistic about if we can do a general science with the impact that we are talking about. I mean about maybe developing a Mexican version of the quantum computer. I don't know if this is possible, okay? But I think that resources is not the only thing that we need. I think that the way that we do science is also not the most appropriate one. So I think that a very important ingredient is that the scientists have enough time, and when I say enough time, I'm saying more than 60 or 70% of their time in thinking in problems. But if you are thinking in, oh, I have to apply for 3,000 different projects because the amount of money they give is not so high, and I have to do this bureaucratic thing that is very complicated, and if your mind is taken away into these more pedestrian problems, and if you are not thinking in science, and if you are not choosing the very ambitious and problems, okay, I don't know, I know that, for instance, it's just a stupid example, but high temperature superconductivity is a super important problem. I don't know how many people in Mexico is really trying to solve the problem. I don't know, it's just a question.
At the beginning there were a lot, and when they saw they couldn't do anything, like in the rest of the world, they leave the problem. No? When the high TC temperature superconducting was discovered, everyone tried to solve it, and then they saw it was very difficult, and but that is a worldwide. They can correct me that it's here, but this happens. If the problem is very difficult, you go to another problem. But it is not just a question of money in that case, I think, in that example. That is my.
Okay, and if you allow me to do a final remark, because it seems that maybe I'm personally complaining, and maybe it's true. Maybe I'm just saying my personal problems and nobody else shared them. But I think that something that makes Mexico also not so competitive in doing science is the time scales. Okay, so I know that if you go to many labs around the world, in the United States and in Europe, and if something breaks in your lab, a mirror breaks, a $40 mirror breaks, you cannot do anything. You need that mirror, okay? And I know that in some labs in the world, you pick up the phone, you call Thor Labs or any other company, I need this mirror. Yes, and you have it few days later, but in Mexico you have to wait months. I mean, I have equipment in my lab that took 1 year to arrive to the lab, okay? And I have a laser which is I was talking yesterday about quantum turbulence, and I have not excited vortices because the laser I need broke, okay? And it took eight months for the laser to go to the company, be fixed, and come back to Mexico. But the thing that happened in the company took 2 weeks, okay? The rest of the time was the bureaucratic process of sending the laser, moving the money from the proper, because the money is divided in money to buy equipment, money to buy materials, money to go to trips. So you have to move. If you have you have to move the money, and there is a bureaucratic process to do that. It took 1 month only to move the money that I had available from somewhere else to the right type of. I don't know how to translate partida. Sorry, but you understand what I mean. So I think that
I think that we understand that. Yeah.
Okay, and this is it.
Okay. I don't know. Pepe wants to say something, but it's had to.
Yes, it's quickly. I agree completely with you, but I mean, from a historical point of view, there has been a quantum jump in the way we do science in the last 15 years. So, in that regard, we are in the first excited state. I know that we have to be ionized, but we are at least making some progress.
I'd like to finish saying thank you, and I hope we are not so pessimistic as we can continue. Thank you very much.
Okay, thank you very much. So, really, we are getting to close the workshop. Please come with me. So, as organizers of this international workshop on quantum technologies, we would like to thank you, all of you, for your great support, particularly to our guests, international guests. So thank you very much for your talks, great science. So we are learning a lot from your experience. So thank you, see you. I don't know, probably next year. It depends on money, right? So please, I would like to invite to come Raúl Iturralde, who is the General Director of Science and Technology Council in Querétaro. He is responsible to be here in these 2 days. He brings the money to be here. So thank you very much, Raúl. Muchas gracias. Do you want to say something?
Bien, buenas tardes a todos ustedes. Solamente quisiera agradecer al doctor Mauricio López Romero, director de la Unidad Querétaro del Cinvestav, la organización de este magnífico evento, de este primer taller internacional de tecnologías cuánticas, que sin lugar a dudas ha sido de gran interés para Querétaro como ciudad y como estado, y cobra una gran relevancia a nivel nacional e internacional el que eventos de esta calidad, a donde asiste un premio Nobel de Física de 1997, destaca Querétaro en cuanto a centros de investigación, en cuanto a número de investigadores, en cuanto a realizar investigaciones, digamos, de vanguardia. Y entonces para nosotros en el Consejo de Ciencia y Tecnología pues es realmente relevante que estén todos ustedes aquí trabajando estos temas tan importantes. Muchas gracias a todos ustedes. Buenas tardes.